Let's start on the next notebook, 12, working with GeoPandas. Once Pandas were invented and everybody started using it, the folks doing geospatial work were very envious of all the data scientists who had this amazing tool that you can do these things very easily. And the geospatial scientists were still stuck with doing loops and iterations and all of this. And it was still quite painful. If you have ever done Python analysis with geospatial, you had to use GDAL and OGR libraries. Those libraries were written in C++. They didn't have a proper Python API. So the code looked very weird. You had to do the memory management. It was not as fun as what we did with Pandas. So what GeoPandas project decided that they will take the Pandas structure and say, our geospatial data is actually just a tabular data. What's different is we need to store a geometry. So we need to way to represent points, lines, polygons. We need to represent CRS. So we need to deal with projections. And we have attribute table, which we can use Pandas. So we can extend Pandas and we'll make it support stuff that we do as geospatial. So GeoPandas was invented. This is one of the core libraries for doing GIS using Pandas. And it's built on Pandas. So everything that you learned in Pandas still applies, but you now have more stuff. So you can read geospatial formats and you can write geospatial formats as well. Let's learn a bit more about GeoPandas. When you installed GeoPandas, some of you had problems. This is because GeoPandas is not inventing the wheel from scratch. It is saying, Pandas already has all the stuff we need. We need to add stuff for support for stuff doing geospatial. So we need to know, given some geometries, how we do buffers, intersections, relations between different objects, and so on. It uses a Python library called Shapely for doing all geometric operations. So when you install GeoPandas, you also install Shapely. And when you do any intersections or buffers, etc., it's using Shapely for doing that. So again, it just takes that and makes it available in this Geodataframe format. You need to know about projections. You say, I want to take my one layer, reproject it, or convert between projections or assign projections. There's a library called PyProj, which it uses for projections. Geospatial data has so many formats. Again, it doesn't invent all its format. This says, I can read any format that is read by GDAL and OGR, which is literally hundreds of formats. There's a Python library called Fiona, which allows you to use GDAL to read different libraries. So it uses Fiona under the hood. When you say, open this dataset, it asks Fiona to open it. Fiona will ask GDAL to open it, and it'll open that. But you get a nice clean API. So again, when you install GeoPandas, you need to install GDAL, Fiona, PyProj, Shapely, which in turn installs a bunch of things. So that's why sometimes installation of this is complicated, and we prefer Conda for managing all these dependencies. This is also helpful for you to know when you are trying to read, say, I'm trying to read a PostGIS database from my Geo Package, GeoPandas. How do I specify some parameters? You'll go to GeoPandas documentation, and maybe the documentation has only like the basic stuff. If you want more advanced stuff, well, you go to Fiona's documentation because it's using Fiona. And Fiona will say, okay, I have this parameter, you can specify it here. Even if you don't find in Fiona, you'll go to GDA's documentation for really more advanced stuff, because it's just using all of that internally. So just knowing what the library is built on top of will help you learn some advanced operations as you go forward. GeoPandas is kind of meant as a general purpose geospatial analysis library. You can do all your standard geospatial geoprocessing, buffers, intersections, resolve. You can do all joins, table joins, spatial joins, etc. You can do reproject, filter, format conversion, all the kind of standard GIS stuff, which you can do using GeoPandas. All of this is in addition to all the stuff that Pandas provides. So all the Pandas stuff is available. So now you have a geospatial time series. You can read it in GeoPandas, apply Pandas time series processing on that, because all of this is available. So all of this is in addition to all the stuff that Pandas has. So again, that means you have your full-fledged GIS toolkit available in Python through GeoPandas, and it uses the same concept as Pandas. So in GeoPandas, you have the same thing. Instead of a data frame, you have a geodata and geodata is a data frame with a geometry object. So your points, lines, polygons will become another column in the data frame. So when you read a shapefile, you'll get a geodata frame. Your shapes will become one column called geometry. Your attribute table will become the data frame. You have a geo series, which is just one of the rows and columns. So And there's a special, when you read any geospatial data using GeoPandas, you'll get one series called geometry, which will have the geometry of that particular dataset. Okay. So with that terminology, let's learn and solve a problem using GeoPandas. We're going to solve a fairly complex spatial analysis problem. I will give you a preview of what the problem is. And this is the problem I teach in my advanced QGIS class. So I teach how to use QGIS to solve this. We're going to take the same problem and see how we can solve this using Pandas and Python, no QGIS involved. So we'll kind of do an advanced geospatial analysis, but now completely within Python. This is QGIS. I'm just using it to show you what the data looks like. In your data package, we have this one Geo package. It's got two layers. First, we have this layer, Karnataka major roads. So this is a state in India, and these are the major roads downloaded from OpenStreetMap. So you can see this is a vector layer of all the major roads in this one entire state. It's a fairly large data set. If I check, it says there are 44,000 features. If you look at the attribute table, it's you have a lot of attributes about the roads. So the problem that we want to solve is, in this state, what is the total length of national highways? We have this column called ref, which has information whether this one is a state highway or a national highway. So national highways are like interstate highways in the US, or like autobahns. They are like the top level highways. State highways are kind of the next level, and so on. So what we want to do is we want to say, in this state, what's the length of national highways? Right? So that means we need to take this first, we need to read this Geo Package file, which is a spatial data format. We need to filter this to have only lines which are national highways, and then compute the length of that. Once we have that, we also want to solve that. We have one more layer here where we have polygons representing the different admin units. So this is admin 2 units of the state. What we want to learn is, in this admin units, we have just the name of the district. So for each district, we want to know that for each district, what is the length of national highway within each district. Okay, so this requires us to do some spatial joins and say, I know each road, I want to find out all the roads that fall within each polygon and compute its length. It is a fairly complex spatial analysis problem. We'll use GeoPandas to solve it, and then compare the results again, what we did using QGIS. So working on notebook 12, we import GeoPandas. By convention, we import it as GPD. You can use any convention. We imported Pandas as PD. We import GeoPandas as GPD. We define the path to our Geo package. So Geo package is a model open format. It is similar to a geodatabase. Geodatabase is a proprietary format that Esri invented. This is an open format, which is used by the community. It's a community standard. It's also an OGC standard. Also, it's a default format that is used by QGIS. It's a much more robust and extensible format than shapefiles. So if you're using shapefiles, stop using them, switch to Geo package. Advantages are, shapefiles has a lot of limitations. You can have only columns which are 8 character wide. You cannot store data more than 256 characters into each field. Also, a bunch of other problems with shapefiles. Geo package doesn't have all these limitations. It can also store multiple layers in a single file. So a Geo package will be just a single file. So if you see on disk, you'll see this is a single file. You can store multiple data layers within each file. You can store raster, vector, tiles, everything within a single file. So you can just send one file which contains all the data. Esri products can also read Geo packages. So I mean, it's portable. Also, it's a great data storage format because you can back up one file and all your data is backed. It's also backed by a database. So it's backed by the Spatialite database. So it's a file-based database. So you get advantages of all the databases, spatial indices, queries, and all the kind of things the databases offer, but in a file format. So it's very fast, efficient, and it's a preferred format for working with geospatial data. So I recommend all of you use that as a storage format. You will have a format that can store the data losslessly. Backing up is easy. When your client or customer asks for shapefiles, you can always convert it and give it to them. But as a storage and data management format, GeoPackage offers you a lot more flexibility. So we will read this GeoPackage first using GeoPandas. Similar to how Pandas, we can just read a file. We can have a function gpd.read file. You can give a path to the file. So here we give the path. Since Geo Packages can have multiple layers, we also give the layer names here. If you have just a shapefile, you can just say read file, give it the name of the shapefile, and you can read that. When you say gpd.read file, what you get is a Geodataframe. And let's see what we get. So once the GeoPandas has read this and stored this, we can now just view this just like a Pandas data frame. And you can look at this preview as with Pandas data frame. It'll show you the first 5 rows, last 5 rows. It'll show you 44,000 rows, 11 columns. But notice what's different here than your Pandas data frame. We have this extra geometry column. So this is our attribute table, and your shapes are stored in this geometry column. So this is the Geodataframe. And if you check the type of this, this is a GeoPandas Geodataframe. Okay? It's just an extension of the data frame format. Geodataframe has these 2 extra things. One is your attribute table, plus it has got this thing called geometry. So if I can just say dot geometry, it'll give you the geometry column, which is your data stored as the geometry. What extra thing it has is also a CRS. You say, what is a CRS? So this comes with EPSG 4326. This is the CRS of this. So a Geodataframe is nothing but a Pandas data frame with a geometry column and a CRS. That makes it a Geodataframe. Okay, let's go to the workflow. First step, we want to now select all the roads. We want to get the total length of national highways in the state. So we use the ref column and say, wherever the ref column starts with NH, that's select all the rows. We can apply the same Pandas filter syntax. We can say, I want to apply a filter on this roads GDF. Same thing, open brackets. And inside of that, we write the condition. So the condition is our roads, the ref column dot str. We learned about str. It gives you, allows you to match string using the str operator. We say starts with NH. So this one just says any row where the value of the ref column starts with NH, the caret says it has to be in the beginning equals to true. So if this condition matches, you use that. So let's apply the filter. One of the things you'll notice is when you do this thing in GIS, right, it'll be a progress bar. Like there'll be a progress bar, applying and selecting, creating a new layer or something. In GeoPandas, it's almost instant. Apply a filter, and you see that you can see now all of this have applied with the ref column. It also makes working in the Jupyter environment much better, because when you're writing this code, you are doing this interactively. You say, let me read this data. Okay, I've read this data, and I want to do this next. If you write in another environment, you have to do the whole code again. Every time you run it, you'll start from import, read it, and apply a filter. That means if this was a very large file, you spend 5 minutes reading it, you'll have to read it again every time you run the code. In Jupyter, you run it once, it's there, you do the next step. So for this iterative kind of analysis, Jupyter provides you with much nicer environment to do this. So almost always when I'm developing a workflow using Python, I'm in this environment. Once I have my workflow, I can put this in a script and automate it and run it elsewhere. But for development, this is a much nicer workflow. Next, we have our national highways. We want to compute the length of each national highways. We have each segment of the national highway here. We have the geometry. We can just compute the length of this. But we have a problem that this data is in the CRS 4326, which is in lat long. Those lat long units are not suitable for doing any computations. So when you compute lengths or distances in the GIS, you do not work with any geographic CRS like EPSG 4326. You need to reproject the data into a projected CRS. So we'll take this data, we'll reproject it to a projected CRS. You can choose any projected CRS that makes sense for your region, for your country. UTM is a good choice. So UTM has different zones. You can pick the CRS there. You can choose 3857, which is the web Mercator, which is a global projected CRS. But you need to get to a projected CRS, and then you can compute the length. So our CRS is 4326, which is lat long. We want to convert it. GeoPandas has this function to CRS. So we take this data and we say, convert it to this CRS. This is the EPSG code for the UTM projection for this particular region. And just do and say, let's check the results. But the reprojection is done. You see the difference now, same data. Here we had coordinates of the roads in lat-long coordinates. Here we have it in UTM coordinates. So they become in meters. So now the unit of the CRS is in meters. Okay, so we did the reprojection. And now we just want to compute the length. We can just say, take the geometry dot length. So this is a built-in method to access the length of this. So we add a new column, roads reprojected length, and get the length of each segment. So you can see now we have a new column, which is the length of each segment in meters. So what's the length, total length of national highways in this state? Well, we're just one step away from answering the question. We started with all the data, filtered all the national highways, reprojected the data. Now we computed the length, we have the lengths, we can just sum it up. So we can just say length.sum. This is the total length in meters, divide by 1,000, and we have the answer 8616.166 kilometers. And this is the length of national highways in kilometers in the state. And this was just 4 statements. If you just go back and just say, read the data, filter it, add a new length column, and sum it up. And the total workflow would be at least 5 to 10x faster than doing it in the GIS, because it just uses pandas under the hood to speed up the workflows. I want to show you the result from my advanced QGIS course, the same data set, same answer, 8616 kilometers. Right? We just do the same workflow in QGIS and we get the same answer. Here we are doing this in Python. This is suitable for automation. We had somebody who took this class and got so excited. They took the project saying that, we are mapping different countries in our organization, and they built a dashboard using this method and saying every week we'll display what the total length of roads mapped in each country. And, you can use this kind of workflow to build a dashboard. Next, we want to say, I have all the national highways, but I want to compute the lengths for each district. So we have our layer for districts. We have the name of the districts in this district column, but that's all it is. Our roads do not know which district they fall in. Our district do not know what roads they fall in. But they have a relation with each other because they are both aligned at the same place. So we can use that spatial relationship and say, can we do a spatial join? And for each road here, let me just display this in a better color. Say for each road here, we will say which is the district that it intersects with and add its attribute. So we have the roads data. If we have the name of the district that this road falls in, we can use this to compute and say what's the length of road in each of the districts. And we can do a group statistics to compare that. So to do the join, we will use GeoPandas, and let's see how we can do the spatial join. One of the great things about pandas and GeoPandas, both have excellent documentation. So they have documentation which is extensive, also had a lot of code samples. So I often find myself referring to those and say, I want to do something with GeoPandas. Let's just go to the documentation and see this. So let's open the documentation. It has got stuff. If you want to create maps and plotting, you can use this. If you want to understand about projections, you can do this. Geocoding, sampling points, all of this, you can learn how to do this using GeoPandas. We're going to open the section on merging data. This is how to do joins. If you want to just do a table join. So I have one spatial data, I want to join a table based on the same column. The function that we use is a function called merge. So one data frame, merge another data frame, and it'll join both of them at the common attribute. So this is a table join. If you're working with census data, this is what you do to do a table join in GeoPandas. We are doing the spatial joins. Spatial joins when we have 2 vector layers and you want to join them based on the spatial relationship. The function to do this is sjoin. The sjoin function has 2 parameters. how do you want to join them? So say intersect contains, disjoint all the spatial predicates that you have. And the second one is what do you want to retain in the output? And a left join will keep the features of the input and extend it using all the matching attributes of the second one. Right join will keep the attributes of the second data frame and discard all the stuff that is not found in the first one. Inner join is the intersection of both. It'll only keep the records that match in both layers. So typically when you do joins in a GIS environment, they're all left joins. So if I show you the equivalent in QGIS, so if I say join attribute by location, this is the spatial join tool that comes with QGIS. You'll say, take my first layer, join it with the second layer using any of these predicates. So these are all available in GeoPandas. You'll say, does it intersect? Does it overlap? Whatever, you can select that. And when you say, what's the join type? The standard one is, you take the input feature and find the matching feature for each of them. And you'll discard stuff that is not joined. So this is a left join. So in a GIS thing, typically you do a left join. In some cases, if you want to do an inner join, that also is fine, where it will not discard the record where there was no match. So let's implement this in our code. Let's get the districts file. So this is the district GDF that we saw. This is the second layer. We just create this as a data frame. So you can see this one has the geometry of a polygon and name of each district. The CRS is the same as 4326. So we just reproject it first. So we reproject it. And now we do the spatial join. So we can say, take our roads, join it with the districts, do the left join using the intersect relationship. So let's run this. Done. Our spatial join is done. So for each road, now you have the district that it belongs to. It just did the spatial join based on the intersection relationship. And now we have the district and length. So we can just say, give me the sum of the column length by district. This is called a group statistics. So you can use this. Now, if you come to GeoPandas documentation and search how to do group stats, you'll not find any answer. So when you work in a problem, say, I want to do group stats. How do I do this? I have a Geodataframe. So you search the GeoPandas documentation. If you don't find it, you say, how do I do group stats in Pandas? Because ultimately, everything is built on Pandas. So all the Pandas functions still work here. So if you go to Pandas, Pandas has extensive documentation on how to do group stats. So we'll take this and say, take our joint data frame, group by district. So for each district, group all the rows that belong to the same district, take the length column and give me the sum of that. And divide by 1,000. So this will give you the sum of length of roads for each district. And group stats are super fast, blazingly fast in Pandas. So again, you can see it went very fast because it's highly optimized. So whenever you find yourself doing some statistics or some data processing, and you don't find stuff for GeoPandas, search how to do this in Pandas. It's the same thing, and you get this. What you get here is just a series, and we can just write it to our output. So we can just write it, and now we have our output, and say length of national highways by each district as a CSV file, what we computed using GeoPandas. So now you can think of the whole workflow is probably just 10 lines. If you just remove all the prints and everything, just 10 lines, read the 2 layers, reproject them, filter it, do a join, and then summarize them using group stats. And you can now implement the whole thing Python using GeoPandas.